You can go ahead. Thank you.
Bon dia, benvinguts, benvingudes, buenos días, bienvenidos. Hoy tenemos con nosotros a Gonzalo Tancredi desde la Universidad de la República de Uruguay y voy a pasar a hacer la presentación de su trayectoria antes de que comience su charla. Voy a pasar a cambio a inglés para que esto sea accesible a todos nuestros oyentes. So welcome everybody. Today we have with us Professor Gonzalo Tancredi. He's a full professor and the director of the astronomy department of the Faculty of Sciences at the University of the Republic, Uruguay. He graduated in astronomy from Universidad de la República and Uppsala University in Sweden. In general, his areas of interest are planetary sciences. In particular, through his career, in 2006, he participated in the proposal made of the new definition of a planet that was accepted by the astronomical community, and as consequence of that, Pluto was reclassified as a dwarf planet. He chaired the Division of Planetary Sciences and Astrobiology of the International Astronomical Union between 2018 and 2021. He has been a member of the NASA DART mission team that impacted an asteroid in 2022. And particularly, he's now involved in a lot of work because from 2021 to now, he has been really busy organizing a national association of researchers in Uruguay. Now he's a former president of this association, so good luck. And this association is called Investiga Uruguay or something. And in particular, as a recognition of all the work has been made on minor planets and minor bodies of the solar system, an asteroid, that is the number 5088, Tancredi, has been named after him. And in particular now, today, we are very glad having Gonzalo here. He was forming part of the tribunal of the PhD thesis of Eloy Peña Asensio, and that was a good excuse to bring this talk a little bit at the last moment, in which Gonzalo will explain us the development of a new fiber network in Uruguay, with the main goal to study bright meteors and particularly these fireballs that sometimes made us a very nice present as a shape of a meteorite. Okay, welcome, Gonzalo, and please keep going.
Okay, well, thank you very much, Jose Maria, and all the other participants of this meeting. I'm very glad to be here. I'm a little afraid of giving this talk after the extraordinary presentation by Eloy yesterday, because this talk will deal with several topics very close to what Eloy has present, but in a different status, and we are just starting our network. So I will talk about the national network of bolide detection or fireball detection. It's called Bocosur. It means bólidos del cono sur, and I will explain why we are talking about bólidos in the cono sur, in the south cone. The motivation of this is that, well, the region in South America has very interesting case of different meteorites and meteor events. In particular, for example, we have the big stream field of Campo del Cielo. It's in the north part of Argentina, in the Chaco. You have several meteorites of this size, of the order of several thousand kilos, several tons, and it's very worth to visit. I did it last year, and well, obviously this was a consequence of a big fireball, maybe a few 10,000 years ago. In addition, we have the impact event of Caracas that we talked yesterday. It occurred in September 15, 2007. It created this small crater, 13.5-meter craters. We recovered a few meteorites, ordinary chondrite meters around. You can see some local people searching for meteorites in the area. This house, for example, was impacted by the debris. It occurred very close to the Titicaca Lake at over 4,000 meters. So doing field work in this condition is not very easy. And in particular, we can ask Pete Schultz that where we sat, and we almost lost him during this work. Another case it occurred in 2015, September. Meteorite went through the roof of this house and impacted the bed. It was recovered here, and the TV set was broken. You can see the broken TV set due to maybe not a part of the meteor, but a fragment of the roof. And we recovered this ordinary chondrite meteorite. And well, you can see the typical things of a meteorite, the fusion cross, the red maglites, but also some particular things like part of the roof. This white part, it's part of the roof. And another interesting case that we were discussing with Jose Maria was the recovery of some tektites in the area of Uruguay. These are other tektites, but this is from Uruguay. And so based on all this idea and all this material and all this research, we decided that it's these are the tektites, and this is the area where it has been recovered in the southwest part of Uruguay. This is Montevideo, this is Buenos Aires, and this area. And these tektites are called Uruguayites. And so, as I said, based on this, we have been doing a lot of outreach activities. And in particular, we have got a lot of material. I was talking with Jose Maria, maybe over hundreds of pieces of material that came to our laboratory, our department, saying that, okay, we have a meteorite. So we decided to copy this flow chart that was developed by Maria Elizabeth Zucolotto from Brazil. And in order to try to discard or to take away most of the cases, because only there are very few cases where it is worth to do some analysis of, and well, like the one that we did for the case of the meteorite of San Carlos. But we think that another interesting field of research is to analyze the meteors, the bolides, and finally try to recover some meteorite to have some fresh material. So I will not go through all the things that Eloy has already mentioned, the introduction about the distinction between the parent bodies, the meteorites, the meteors, the fireballs, and finally, the recovery of meteorites on the ground. From this, I would like to remind you that the meteor event, occurs start at these altitudes of the order of 100 kilometers down to maybe 80 kilometers or even 40 or even 20 kilometers of the bright part of the event, of the part where we can see it on the sky. This dark part, dark flight, it's at altitude below 20 kilometers, 30 kilometers, and when we recover the meteorite on the grounds, it has traveled a distance of maybe 20, 30 kilometers in a totally dark event. So this is the status about different fireball networks. This plot, this map is maybe a little bit not realistic in the sense that we paint different countries with the different kind of fireball network that already exists, but in many countries there are just one or two or very few stations. I will go back to this, but we have a very dense network in France, in Spain, in the south part of Australia, and some sporadic stations in US, Canada, Brazil, and very little in this region. So you can see that all the skies are not distributed homogeneously uniform in our world. We have many dense stations in the north part of the world, in the northern hemisphere, very few in the south, and it makes a problem with the recovery of meteorite because, for example, there are very few orbits with well-known meteorite recovery with well-known orbits, only maybe a few tens, and only 9 of them are recovered in the southern hemisphere, 6 in Australia, 2 in Brazil, and 1 in Botswana. So there is a big asymmetry between the north and the south. That's the reason to lead this national detection network of bolides. Bocosur, as I say, it means bólidos del Cono Sur. Who we are? Well, now we come with the names. My name is Gonzalo Tancredi. The co-PI of the project is Manuel Caldas. We have several master and undergraduate students. We have also a strong collaboration with the high school, and in particular with the teachers, astronomy teachers in the high school, the also high school observatory Montevideo, and another observatory that belongs to the Ministry of Education, and also collaboration with colleagues from the Faculty of Engineering. From the finance, we got finance from CSIC. It's a Comisión Sectorial de Investigación Científica of our university. From PDCIVA, it's a Programa para el Desarrollo de las Ciencias Básicas. From the US Embassy, and as I said before, collaboration with these other institutions. The motivation is to, well, do a scientific study of bolides and meteorites, meteors, to install a network and to do a science, community science project with the collaboration of students of and teachers of the secondary school. And that's why, for example, we give lectures in many schools and many high schools. And you see that this was done during the pandemic. Most of the network has been developed during the pandemic. Well, what is the hardware of the network? We have stations. Each station has this facility. It has a box with a CMOS camera, this one, with a fisheye lens, a dome, and mini PC with a SSD disk, a GPS. It's just here, a GPS sensor, connection to internet, a temperature sensor, heater to prevent dew, fan to cool the system, and well, and the total cost is on the order of $1,300, so a little bit more than 1,000 euros. The stations were very planned to where they will be installed. And to do that, what we consider is that if we consider that we would like to see the event at altitudes between, let's say, 100 kilometers up to 60 of a few tens kilometers, and we have a field of view of the effective field of view of the order of 120 degrees, that means a zenithal distance up to 60 degrees, then the separation between the stations should be on the order of 100 kilometers. Okay, and that's how we located all the stations. These circles are of 100 kilometers, and this corresponds to the first five or six stations that we have. And what is called the red part is the area covered by our one station. The green part, the area covered by two stations, and the blue part, the area covered by two stations up to this considerations here of this calculation. So you can see that most of the area is covered by 2 or 3 stations. Now we have 20 stations. We just finished to install them in February this year. Most of the stations, I would say 19 of them are installed in the roof of high schools. All these are cities, capitals or main cities in Montevideo. They are separated between 100 and 120 kilometers. So we were choosing each city. We choose, well, the cities because they have high school, liceos, where we can have teachers and students interested in the project. We can have local people that could help us in solving some of the easy problems. Also, we can do some outreach activity with them, and they have good internet connections and good and stable electrical connection. As you see, it covers the entire Uruguay. Uruguay is located here, small country. The first station was located in the roof of our faculty, but the other ones, the other 19, were located in different high schools. Here you can see our students working in the location on this install of all the stations. This was the last one. In order to have a comparison, here you have Spain, here you have Uruguay. I would say Uruguay is something like 1/4 of Spain or a little bit less. These are the location of the Spanish meteor network. and this is the location of our. What we decided is that we have a dense cover and let's say to be as much uniform as we can do it. And I think that that's a big advantage because we were able to cover the entire country. And if you compare, for example, with other networks, well, France is I think it's a little bit bigger than Spain, and it has many stations. But here, for example, in Australia, as you know, Australia is much bigger, and you have very few stations, only just ones located here and somewhere here. The American network, it's very spread apart. The Canadian network is only just a few stations in this area. And the other networks I didn't put it, the other networks in South America, the one in Brazil, it's very distributed in this very huge country that is Brazil, and this is similar with the case of Chile, because Chile it's almost a line, and so they only have a few stations in some places. So I think one of the advantages, or the two advantages, is that we are using the same hardware for all the stations, and we are having the stations uniformly distributed on the country. We have developed some software for the operation, for monitoring the activity of the station, for the post-processing, and from the automatic classification of the data. For the operation of the station, we have developed this interface, Poly.UE, that it can control the camera, the motion, the initial motion detection. This Poly.UE, it runs on each station and is developed in MATLAB. This is the interface, and this is the image. It's completely blank because it was taken during the day. But you can set here different parameters and or just load the set and it start running automatically. We have a software for monitoring the network. The software runs in each station, and it communicates to the central server, and then it publishes the information in a web server. It's called Sentinella, and it gives us the status, some snapshot every 3 minutes, and it produces a time lapse every night. And as I said, it runs. You can, I think, in order to see, I have to stop here and share where is, I think this one. Yeah. For example, it keeps this status that this is most for our internal information. It has information about the date, the time, and the status of each of the 20 stations. But most interested in this one, this is the public version of this. It's a resume. Well, it's updated every minute, or every 3 minutes. So this is it's saying that it's the day on the date, and for example, this is the last image of the night of this QT, and you can have, well, in this case it was covered, so you have the 20 station here, and every morning it produces a time lapse of the station. So you can see whether it's covered or not. Okay, I'm gonna go back to this. And Then we have a software for the post-processing that it can do the astrometric and photometric redaction and processing to process the detected fireballs. It's also developed in this case in MATLAB. And for that, we use an astrometric redaction, and we don't go through the equations. It's similar to the equations that was shown by Eloy. This is for the astrometric redaction, and this is for the photometry. Well, many cases we have a saturated search because the fireball is very bright, so we have to do some kind of adjustment to get a reasonable estimate of the brightness, taking into account the saturation. And well, I will present some results. We have a paper in the revision process, hopefully the last step of the revision process. And for example, in this paper, we present a comparison between two sets that it's at the beginning, we use another camera, as I didn't mention that. At the beginning, we use the video camera WATEC, but now we have moved to a CMOS camera ASI of ZWO, Chinese one. And you can see here that this gives us a better improvement in the astrometric reduction. The error in the astrometric reduction has been reduced from 15 arc-minute pixels to no, sorry, this is the resolution, and the reduction has been reduced from these values, depending on the number of the stars, down to these values. So we make a large increasement of the astrometric resolution. Also, the photometry is much better. The ASI camera, it's much sensitive than the WATEC camera. This is a case, for example, of an event detected on October 2022, and the kind of photometry that we can do. And for example, well, this is the result of this event, the evolution of the height, absolute magnitude, distance along the trajectory, and velocity. And this event, well, using the method of intersecting planes by Sepleca, we obtained that the radian it's close to the northern Taurus, so it might be from cometary origin. What else? Okay, yeah, this is the plot that we produced for that event. This is the kind of videos, yes, for example, produced. This is a typical meteor, but we have also planes, in particular in the station in Montevideo, because it's in the way to the airport. So we have a lot of planes, but we have also some animals. Yeah, there you have an insect. Or even, well, some clouds that could trigger the system. And right here we have another meteor. We have the full moon, or close to the full moon and the meteor. There we have, I think, a nice bird. And we have clouds, or even thunderstorms, and some events that could trigger the system. So we are producing a lot of videos, and we have to classify them. For example, we have over 250,000 videos of the WATEC, and now we might have over 200,000 videos from ASI, and it keeps growing. We produce on the order of that, and obviously most of this is just rubbish. So we need a way to classify them. And obviously the manual way is not the way. So we have to develop some kind of machine learning solution. But for the machine learning, as you may know, you need to train it. You need to say at the beginning which are bolides and which are not. So for that, we have done part of the work by ourselves, but we have the collaboration with the secondary students and teachers. And we have developed some workshops to train them how to classify. In particular, we have already developed 4 workshops. All of them were through Zoom. In this workshop, we teach them about the science of meteors, the work, how to operate the stations and the network, and how to classify manually the videos. For example, we have on the order of 150 participants, and most of them complete all the activities. Maybe 50% of them complete the activities. They have already classified several 100,000 of videos and detected many meteors. And the participants continue collaborating with us. We gave them some certificates to show the work that they have done. Recently, we have developed a web application to make this classification more easily. And I will show you how it works. Share screen. Google Chrome. Yeah, this is the interface. You will have let's sure. You have a video and you have to say if it's a bolide or not. This seems to be a plane. I will put no. And then it gives you another video. And it keeps running. You have some light here, but it doesn't seem to be a bolide. So I put no. I can also add some comments. And then another plane here. So it keeps running, I mean, uploading videos. There you have something, but, well, I don't know what it is. It's going quite fast. And it's less than a month that we produce this. And we hope that this year, many teachers of the high schools will show to their students this facility, and they will start working with us in classifying. In addition, we have the possibility to report the events that you can see, for example, by chance, and either we have a web form to produce that, or we have a link to the IMO report. And the idea is that this will help us in the automatic classification. We have already a version of a machine learning algorithm. It's called AutoBol, and was developed by students of the Faculty of Engineering as the final project. It is based on a method for automatic machine learning, a supervised automatic machine learning, and using this XGBoost, extreme gradient boosting. And we have now another student, it's an Uruguayan student, but remotely working at the University of Granada, and he's using deep learning algorithms to do the classification. as we were talking yesterday during the Eloy presentation, it would be nice to collaborate, because it's not necessary to do the work many times, because if it's already performing well, then these first versions, I would say that we are not very happy with the performance. So that's why we decided to go for a new version. In particular, Autoball, this automatic works in the following way. Well, it takes the video, obtaining individual frames, make a primary detection, locate the area of interest, make a determination of the trajectory of the path, and for that it used this ransack method to identify the path. And from this path, it generates a few parameters, and it uses this parameter for so it's different characteristics and to the classification. For example, depending on different set of parameters, it makes the classification. It may have, but I would say that we are still testing a recall of this order and a precision of this order, but this was at least in the initial presentation, but now we are running in a much larger database and we are not getting these values. So we have to work a little bit more. And for example, these are the kind of classification that it was done. For example, well, this bolide was detected with a 97% of confidence. As I already shown, we have a web page. It's called bolidos.astronomia.edu.ui, Bocosur, where we have information about the workshops, the status of the stations, and the information about the last night. So coming to the end, we have developed deploy a dense national all-sky network for the automatic detection of bolides. We have a processing, either operating and processing tools to analyze the data in all the stages and all the steps from the detection to the trajectory determination. And we are working in automatic classification with some support of manual classification in a work where we combine research and citizen science. And well, one of the problems that we have encountered is that we have to develop better algorithms for triangulation. We can resolve simultaneously the dynamic and physical equations. Okay, so that's the end. Thank you.
Questions? I have a short question. For the ICE-CSIC, what is it total time?
The exposure time, it's on the order of 1/20, well, I would say 1/15th of a second. 1/15. Yeah. It's a little bit longer, but I didn't show the comparison, but it's much better. It's at least 1 or 2 magnitudes of increase in intensity, sensitivity.
Yeah, I understand this number is 12 or 16 in the IC camera. Or not?
In the IC camera, yeah, I don't.
Well, usually with the signals is 12.
Yeah. Yeah, I think it's 12. Yes.
With the working in the video camera, usually you use 8.
Yeah.
Then
yeah. No, it's It has a better sensitivity and resolution that it's much better because we are not using the full frame because that it takes too much time, but the resolution it's increasing by a factor of 4. Well, the astrometric resolution. And for example, yeah, I didn't include that, but with a water camera in a single frame, we only detect 2 or 3 stars, the very bright ones, in a single frame.
Yeah.
And in a water camera, in a single frame, we can detect maybe 15, 20 stars. So adding, well, as it was shown, we can detect hundreds of stars in the ICE camera.
I want to ask you, because having so many stations, and as these stations are GPS controlled, I imagine that you have already think about the particular the use of timing, because every bolide will be starting almost at the same time. If you choose this option of the timing, probably you can remove a lot of videos that can be, or well, spurious data, or detections from only one station. So this could be used. I think it's a way in the moment that you have a video almost in the same second in 4, 5, 6
at least
stations,
2 or 3 stations.
that should be a bolide.
Yeah,
Or could be a re-entry, an artificial bolide, but that could be perhaps a way to
get rid of
the number, because it's a huge number of videos.
No, yeah, I think there are possible improvements in many ways. For example, we can we have a first filter on site, in the sense that we have the operation software, the first one. I didn't explain how it works, but what it has done is that to compare consecutive videos, to consecutive frames. And if it see that there is a difference between the frames, then it start recording. So that's why we detect many things that are not real objects. So combining information, or it would be also possible to run on-site and automatic detection when we have a reliable software for automatic classification, because the software can run easily on the computer. So in that way we can read it, but also we can use information of station at the same time.
Have you think as well in incorporate, in addition to this, to the all sky cameras, that the resolution in fact is not so high, perhaps the use of a small field video cameras to control specific volumes of atmosphere that probably are well covered by the camera, or even in the corners of the network. Perhaps you can set these more highly resolutive cameras that could be
since the beginning, our main objective was to the recovery of meteorites. I mean, to do these fireball, very bright events, and these bright events can be observed with these cameras, maybe with not a very high astrometric resolution, but if we start combining information of 3 or 4 cameras, then I think that we will get a reasonable estimate of the path. We prefer to have the same system in all the other things, that we cannot afford a very high, very expensive system. So as I say before, this costs well, let's say $1,500 for each station. So that's why with a limited budget, we were able to install 20 stations.
It's just an idea because
Yeah.
probably you can involve, as you have started as citizen science, you can involve people for doing this.
Yeah,
We did.
this collaboration with the high school has been very useful because we get the support from them, we get many people interested in the project, and there is a possibility to install more stations because, for example, now many teachers want to have their own station on the roof of their observatory. And in Uruguay, we have, I think it's 80 high school observatories, at least high schools that has a small telescope. And each of these observatories has a teacher with some hours dedicated to the observatory. So one possibility is to extend from these 20 up to 80, for example, because all of them want to have their own observatory. And the other thing that I didn't mention is that now our idea is to start extending our network to the south of Brazil and to Argentina, because all this area, it's a very dense, I would say not dense populated, but we have towns, many towns at distance of the order of 100 kilometers. So it would be possible to go, for example, to the Entre Rios and Santa Fe province and Buenos Aires province and to the Rio Grande do Sul. And so it would be possible to extend. We have already started to talk a little bit to extend it to Paraguay. It's a little bit farther, but they are interested. So, and in collaboration, for example, with Diego Hanches and people from Brazil, it would be possible to start to extend it to start covering the South Cone. That is it's what is called this region of South America.
Thank you for the presentation. I have a question regarding the autoball slide.
Mhm.
Yes, I was curious about the ransack algorithm that's applied for detecting the trace. I never heard about that. Yeah.
Have you heard about the Hof transform?
Yeah.
This is a different way. It's supposed to be better.
Just to
Yeah, in the past I used the Hof transform. The Hof transform, what it does is to, starting from a line in a 2D space, make a transform into a different space phase where this space phase correspond to the equation of the line. For example, the intersect and the angle. These people from the engineer find another algorithms that use these ransack algorithms that identify curves in any kind of 2D images. So I can give you the reference and they have the pieces in Spanish. That's easy for you to understand it. And it explains how it works, this ransack. But the idea is the same. I mean, to find a line or in this case, a curve into a 2D image and define some parameters.
Yeah, so I was wondering about these high schools that are involved. So they're involved in the data collection, but are you also planning to involve them in the analysis of the results or in the scientific interpretation? Because that would be really interesting for them, I guess.
Yeah, well, it depends on the interest of the students. As I said before, we have already given workshop for 150 students. We are repeating this workshop every year, 1 or 2 times. And the first things that we invite them is to do the classification. Okay, we give them hundreds of videos, and we ask them to classify, this is a bolide or This is not a bolide.
But that's still part of the data collection. no?
Sorry?
That's still part of the data collection.
Yeah, that's part of the data.
It's more about this, this interpretation, the scientific.
Well,
Yeah.
that we are talking about students of 15 years, 15 or more or less. It's they're very young.
Sure.
They cannot go through this. I mean, this was done by engineering students.
Right.
It would be possible maybe to go a little farther, for example, to do the triangulation. The triangulation, it may be even possible to do it geometrically, because so it depends on the students. And some of the students have got interested in astronomy, and now we are working. They are working in not working. They are studying astronomy in the university. So it's a way to let's say start doing some kind of citizen science. They also have collaborate with us with the operation of the station. If we have some problems at the station, we can ask them, either the teacher or some of the students, to help us in some things. But if they are really interested to getting into more detail, we are open. Now we have something like a group of, let's say, 6 undergraduate students working with the project. Some of them just of the first years.
So thank you again, Gonzalo, and good luck with the development of the network, and more stations, and over other countries as well.
Okay.
Good luck with meteorites.
Yeah. Thank you. Bueno, entonces esto yo